Hi, so I'm Josh. I'm a software engineer. I work in the Oracle database group. Specifically, my group works on technology in the database related to processing JSON data. So I'm going to start out, I want to warn you in advance, this talk is mostly about Java, but the first couple of sections are kind of focused on the database because it's kind of necessary background information for the Java stuff. So I'm going to start out talking about like why you might want to model your data as JSON and store it as JSON kind of generally, and what the kind of landscape is there for databases. And then I'll talk about how, in section 2, how we solve that problem in relational databases, specifically Oracle database. And then from there on out, it's all the Java stuff. So I'll talk about like how a Java application can interact with the database and store JSON efficiently. So a document store is a type of NoSQL database. In fact, it's the most popular type of NoSQL database. And the big elephant in the room here is MongoDB. And so these databases store JSON or something like JSON. And JSON's this simple format. It has a few types: strings, numbers, booleans, objects, and array. So like on the slide here, there's a example of a JSON object representing a movie, has attributes like the title of the movie, the date, and the cast. And so kind of the notable aspects about storing your data this way is that the types can nest, right? You can store an object with an array with more objects, and that it's self-contained. So like these values can flow around to different nodes in your system and kind of be read independently, without having to consult a data dictionary. And so my group at Oracle, we are not building one of these document stores. Our strategy at Oracle is that we're building a converged database, one database that can handle a bunch of different types of data and a bunch of different workloads over that same data. This is really different than, say, many of our competitors, notably Amazon, right? If you Google Amazon and databases and you get to their marketing page on databases, their messaging is kind of like use the right tool for the right job type messaging, which can sound good and be convincing. But we believe that the reality of that is for non-trivial systems, it leads to systems that are complex and expensive. Like you'll have ETL processes, multiple licenses, security models, and things like that. So to that end, we've been working for the past 15 years at changing the core kernel of Oracle database to be really good at JSON processing. And we're not the only ones doing that. So this is data from a website called dbengines.com. We're not affiliated with them, but they take information from like search engines, LinkedIn, Stack Overflow, stuff like that, and they crunch it all together and come up with a number. And the bigger the number, the more popular the database. And so something like this, obviously, you have to take with a grain of salt. But for whatever it's worth, 7 of the top 10 of these popular databases are these relational multi-model databases like Oracle, MySQL, Postgres, things like that. But the one kind of interesting thing about this list is one of these, the database here at spot number 5, MongoDB, they weren't even here like 5 years ago, but they've come up into the top 5. And these guys rank hundreds of databases. So to make it into spot 5 is significant, right? So there must be something people like about these databases. So the reason people like these document stores is there's like a data model aspect and then there's a performance aspect. So JSON's schema flexible, meaning if you want to take like your Java object and persist it, you can often persist it as JSON without having to define some table in the background and come up with a schema in order to persist your data. So it's a little bit easier to get started. And then you can control that schema from your application, over time as it grows. Like if you want to add some new, field to your class, you can do that without having to talk to a DBA or, modify a table definition. There's less what we call impedance mismatch. So, domain objects, your Java classes might tend to be tree structured. You have different collections stored in them. And you can often map these instances to JSON in a way that kind of looks and is structured more similar to what it looks like in your app. So you're not having to join together different rows and tables in order to kind of materialize your objects. And then finally, there's the whole NoSQL part of it. So Mongo calls this like data as code, that in order to interact with your database, you're just writing more Java code. You're not having to embed these SQL strings into your application code. And so SQL is great for analytics, reporting, and things like that. But if you're just trying to like filter, get, put, kind of do CRUD operations, from a microservice or something like that, SQL may not actually add a whole lot of value. The other aspect with these databases is performance. So databases in this category are often scalable or elastic, meaning is that demands on your application grow. You can scale the database to meet those demands. And they also tend to be used for building interactive applications. So response time is very important. So a lot of these people or databases advertise that they can support single-digit latency at scale. And what they mean by that is that even when a ton of people are accessing the database at the same time, they can keep the response time of those operations under 10 milliseconds. They're also thought of as being, resilient, highly available, and low-cost options. So the goal of our group at Oracle is that we're bringing these benefits, these performance and data model benefits of these NoSQL stores, but we're bringing them to Oracle database, and without losing kind of the traditional strengths of, a relational database like Oracle, ACID, consistency, SQL for analytics and reporting, the ability to normalize your data, and things like that. OK, so there's a few slides here. There's some about how, at the database level, we integrate JSON. So there's about 5 more slides, and then I promise after that, we're going to get to all JSON for the rest. I mean, all Java for the rest of the talk. When you think about the relational model, you probably picture something like this. You've got a schema that contains a bunch of tables. Those tables contain rows. A table is flat, meaning the rows aren't nesting within each other. And the rows have a rigid structure, meaning every row has exactly the same column values. And then if you want to get at those rows, you're going to be writing SQL to access them. And so this is kind of traditionally what people think of when they think of relational database. So how did we add this kind of schema-flexible JSON into this? It's very simple. We just said, OK, we're going to come up with a column type called JSON. So a single column can be of type JSON. And then you can take your flexible data and kind of cram it in one of these columns and have that be flexible. And then we've been working for years now with the ISO SQL standard to make it so that you can query data, JSON data stored in one of those columns. You can query that data using SQL. And so you could have a whole 2-hour talk on this topic. But the basic idea for today is that this is very mature. It's been going on for a long time. And at this point, anything that you're used to being able to do with a relational row, you can also do those same things with a JSON object. So you can project out values. You can filter them. You can index them. You can do joins, aggregation. You can convert between relational and JSON and back. And so there's examples here where it's, the first example is grouping by the genre attribute of a JSON object and then summing the gross sales for that genre. So while we've been doing all this for a long time, there's been some interesting changes that have been happening recently, not only for us, but for other relational databases out there. So when we started this back in 2013, we were having people store these JSON objects as JSON text. But in the past few years, versions 19 and 23 of the database, we've moved away from text storage, and now we're storing this data, this JSON, as a binary encoded format that we call OSON. And we're not the only ones that are doing this. Postgres, MySQL, even SQLite now have binary encodings for JSON. And basically, all the top 10 databases on that slide I showed earlier have some form of a binary encoding for JSON. Now, the next couple of slides are going to explain why we did that. So the first reason we added this binary encoding is to extend the type system. So JSON only has this very simple set of types, string, number, true, false, and null. And we added floating point numbers, timestamps, intervals, and raw values. And so why we wanted these extra types is, one, for fidelity with relational data. So if I have some row, like a row that might be in this table on the slide that has a created attribute with a timestamp, we wanted to be able to take that row, convert it to a JSON object, and back without having to convert that timestamp to a JSON string. And the other reason we wanted these extra types is because that's what MongoDB did. So Mongo's format is called BSON, and if people using MongoDB wanted to bring that data into Oracle database, we wanted to be able to do that without having to strip out all the types. The other reason we wanted this format, maybe more interesting reason, is performance. So OSON is very carefully designed to make it very efficient to both query and ingest. And again, you could have a full 2-hour talk on this, but one of the reasons is pretty simple, is that when you encode the data as this OSON binary format, it tends to be smaller than the BSON or JSON encoding of that same value. So if these documents along here, D1, D2, D3, are different JSON documents that we got from customers. And what this is showing is that when the data tends to be small, it's kind of a wash. It doesn't matter. The JSON text, the BSON, the OSON, it's all about the same size. But as the size increases, it gets into the kilobytes, maybe even megabytes, the OSON tends to be a lot smaller. And so what that means is that there's less bits being sent over the network, and there's less I/O happening on disk. The other reason it helps us with performance is that, unlike other people's binary formats, we designed it to support random access within the image. So imagine that you have this JSON object at the top of the slide representing a movie, the movie Iron Man. And let's say in SQL, I want to pull out the year value of this movie. What OSON allows us to do is that we can jump straight to that year value without having to scan past the name or the genre of that movie. And while it may not matter for a little object like this, if you imagine it going into the kilobytes or maybe megabytes, only having to access a few bytes to get to the data we need and not have to scan through the rest of the document can be a big performance gain. The next thing we do is that when in your Java application you want this value, you want to take it out of the database, we take it as it sits on disk and we ship it over the network. We don't spend any CPU cycles on the server. It just goes straight in this smaller format to your Java application. So there's less I/O going across. And then when it gets into the JVM, we play the same trick that we play on the server. So if you have this object pointing to this movie, and I say, hey, I want to get this year as a Java int, we do exactly the same trick. It doesn't have to convert it to a hash table or a hash map or something in order for you to access it. You can just jump straight to that value as it sits in memory. And so the combination of these three things give extremely low latency access to that first value. So that kind of sets the stage for the rest of the talk, which is all about Java now. But I'm going to talk about the different ways that you can access JSON from Java and what we're doing in the context of the OSON, this binary format, to make those APIs more efficient. So when you're working with JSON from a Java program, normally, the APIs you're using to access that fit into one of three categories. So the first category, streaming, is you're accessing the data in that JSON in kind of as a stream of events. And you're accessing it in a forward-only motion. Most popular JSON parsers like Jackson or JSONP, JavaX.json, Jakarta.json, support some form of a streaming parser and generator. The other form that you often see this is with a DOM or a tree model. And so with this, the JSON document's represented as a tree data structure. You're still accessing the data kind of generically, but you can have random access to any value in that tree by calling methods on the various nodes. And then finally, there's data binding. And so this is maybe, I don't know, I would say maybe the most popular thing I see people use. But here you're just using JSON as a serialization format for the Java objects or Java classes that you create. And so if you have a class representing a movie, something like Jackson Databind will take a JSON object and automatically create an instance of that class for you. And then when you're ready to save it back, it'll automatically take that class instance and convert it back to JSON for storage. There's also a JEP or a JDK enhancement, which is in preview, for adding the middle one, the tree DOM, to the JDK. So if you know where the JDK sandbox is, you can go look at that. But it's in preview mode right now. So what we're doing with these APIs is we're not trying to change them or make different ones, but we're trying to enable you to, instead of using JSON text underneath them, you can use OSON instead. And what that gives you is better performance and this richer type system when you persist it. So the first two, the streaming and the tree model, we put in the core JDBC jar. So on the left here, there's the Maven coordinates. So if you're already using Oracle JDBC, you already have access to the streaming and tree models for OSON. The third one, the Databind, there's a separate plugin we made in the Jackson Databind extensions. And so by putting this other dependency on your class path, we enable you, Jackson, to start working directly over OSON instead of JSON text. So the first two, the streaming and the tree model. For the streaming model, there's basically two interfaces in this package, oracle.sql.json. My thing's not working. But there's two interfaces for that, the parser and the generator. And then with the tree model, there's a bunch of interfaces basically for all the different types that can occur in this tree data structure. And then the third component is a factory where you can instantiate these other things. And so here's an example of, the example's next slide. So when you're using a stream-based interface to read JSON, basically you're calling this parser.next method. And every time you call that, you'll get a new event. And you might get an event for the start of an object, for a key in an object, for the value that follows the key, for the start of an array, and so on. So you're kind of getting these events in a forward-only motion to consume the data in the JSON document. And the generator is basically the reverse of that. In order to create a JSON value, you're writing these events, write start object, write key, write value, and so on. And so most application code wouldn't use these interfaces because it's kind of difficult to consume the data this way. But they're meant for use with building applications that are very performance sensitive. Like if you wanted to build a JSON path parser, you might use these stream-based interfaces. Or if you wanted to consume a JSON document that doesn't fit in the memory of your computer, you can use these, right? Because they don't have to hold the whole document in memory at once. So here's an example. So here, it's creating a file output stream to a file called movie.oson. And then it's wrapping that in one of these generators. And then it writes the events to the generator. So it writes a start object, writes the name, the genre, the created values, and then it writes the end of the object and close. So at the end of running this code, you'd have this file movie.osin containing an OSIN representation of this object. So next onto the tree model. So with a DOM or a tree representation for JSON, you have a tree data structure where each node in the tree corresponds to a value in the document. So in this example, you'd have a node at the root that represents the object as a whole. Then you'd have nodes for the Iron Man, the title of the name of the movie, the created time. You'd have a node for the array and a node for each value in the array. And then if you want to access the value, you call various methods on these different nodes. And so here's an example of that. So it's, again, creating this factory, creates a new object, puts the name, the year, the created, and then prints out some of the values in the object it created. And so it's pretty simple. And these typically implement Java collections. So like an object extends a Java map, an array extends a list. So that's the tree structure. And then finally on to the Databind. So with Databind, again, the goal is to take a Java class and convert it to and from JSON. So when we're considering this mapping with OSIN, there's basically two goals we have here. If we've got some OSIN from a file or in the database, we want to create the instance of this movie class without having to go through some intermediate representation. We don't want to have to convert it to a string first or something like that, or some other in-memory representation. We want to go directly from the OSIN to the class, both for performance reasons and so we don't strip away these extended types. And so here's an example of how you can do this with the Jackson Databind examples. So on the first line here, we've got a record, representing a movie again, and we're instantiating a new version of that movie. And then we create this special version of Object Mapper. So Object Mapper is a normal class you would use in Jackson. But we're getting a version of it that's going to work the same way, but it knows how to generate this OSIN binary format under the covers. And so we basically take that mapper and we call write value, and we pass, the output stream that we want to write the movie to, and the movie is the second argument. And so this is going to take the instance of the movie and it's going to convert it to this OSIN byte array, which could be sent to a database or a file or wherever. And then if you want to read it back from that OSIN, you can call read value on the movie class, and it kind of reconstitutes it. OK, so that's kind of a quick tour of those three APIs. You've got the streaming, you've got the tree model, and then you've got the Databind. But what I haven't talked about yet is how do these different things interact with a database. So JDBC is in the JDK, and it for reading data out, it's already got these get object methods that are kind of generic. And so what we did for adding JSON support there is we just extended get object so that it can work with JSON. The example at this bottom of this slide here is showing executing a query that selects a data column, a JSON column from some movies table. This is kind of normal looking JDBC code at this point. And then as you iterate the result set, the result of that query, on that result set, you can call this get object method. And you can tell it first is the column, in this case, column number 1 that you want to get back. And then the second argument there is the Java type that you want to consume that value as. And so in this case, it's saying, I want to get this as one of these tree model things. But the table there on the right shows all the different types that you can pass there. So you can say, I want to get it as a string. You can say, I want to get it as a streaming API. Or if you have this Jackson extension on your class path, you can also say, I want to get this as my Pojo, my movie class, or whatever it is. And underneath the covers, JDBC will automatically take that OSIN, use Jackson to convert it to whatever type that you request. So if you want to send this data to the database, it's a similar story. So let's start at the bottom of the slide. Here it's preparing a statement, insert into this table and some value. But now we're calling the set object. So it's the first argument of set object is the bind variable that you want to set the data to. In this case, it's the :1. And then the second argument is the value that you want to set. And then the third argument is you're telling it, hey, this is going into a JSON column. Because for performance reasons, when you try to run this insert, we don't do a round trip to the database to figure out what type that column is. So if you, for example, passed a string as that second argument, by telling us the type, the third argument, that it's JSON, that allows us to convert it to OSON and send it to the server efficiently. And yeah, so it's kind of similar types that you can pass in and send to the database. And again, if you have this Jackson extension on the class path, you can just send your own Java objects, straight in and store them in that JSON column. Okay, so that's what we talked about so far. Is we've got the 3 different models for representing JSON in Java. We extended JDBC so that you can send them in and out to JSON columns. And so for the last section I'd like to talk about is Spring Data and JSON. So Spring Data goes like, one way to look at it is a step further from like these Databind examples. They make it so you don't even have to put these SQL statements in your code anymore. So with Spring Data, you're working with the database as often as like a repository of objects with methods that allow you to access the data instead of setting the SQL stuff in your code. And there's different adapters for Spring Data for different databases. Oracle database actually works with these 4 of them. But the concept is similar. So there's an example here on the right where there's a movies repository, and it's calling this method find by ID that Spring added for us. And we just pass in the ID that we want, and Spring Data automatically sends back to us an instance of our movie class. So not only are we not touching the JSON or looking at the JSON at all, but we're also not having to write any SQL either. It's just kind of giving us a programmatic API to our database. And one of these that I want to talk about in this section is Spring Data JDBC. So Spring Data JDBC is implemented directly over the JDBC interfaces. And this adapter is based on a paradigm called domain-driven development. And so the idea here with this is that you're grouping together your entities as an aggregate. And the entities that you put in one of these aggregates are a unit of change. So they get read and written together always. So a classic example is like a purchase order schema. So if I have an order and line items, I might choose to represent those as an aggregate. Because if I drop the order, I probably want to drop the line items too. If I want to make a modification to an order or a line item, it's probably okay that I lock that order and its line items. And we're probably not going to have massive amounts of line items. There's probably going to be relatively few. And so you might choose to make orders and line items together in an aggregate, a unit of change. You wouldn't want to do that with parts and line items, right? If I drop a part, I don't want to drop all the line items with that part or vice versa. So with Spring Data JDBC, let's say that I have a movie and some images for that movie, and I'm going to define that as my aggregate. By default, what you would have to do is you would create a table to store the movie objects, and then you would also create a separate table to contain the images. You'd need the field names and the column names to, by default at least, match up somewhat. And then you'd have a key-foreign key relationship between the images and movies. So image table has the column called movie, which references the primary key of the movies table. And so if you wanted to use these classes with Spring Data JDBC, by default, you'd do something like this. So let's look at what happens now. If I have my movie repo and I want to find one of these movies by its primary key, you get this really sexy looking single line of code to do that. No SQL, no JSON, you just get your movie object back out. However, what's happening underneath the covers, at least by default, is that Spring Data would issue a select query against the movies table, get the value by primary key. And then it would do another select query to get all of the images with that same primary key. And so right away, there's some things to notice here. We're doing multiple round trips to the database. We probably are going to need an index on that foreign key because we don't want it to have to scan all the images to pull back the ones for the movie we want. And so there's going to be at least a couple of round trips here to kind of reconstitute the movie and its images. Let's look at what happens for insert. So again, you have this really simple looking line of code. I just take my movie object, I call save, and it just goes into those two tables. But what it's doing under the covers is it's doing an insert into the movie table, and then it's doing multiple inserts into the image table. So at least a couple of round trips. We're probably doing index maintenance. These are random IOs that are going into two different tables, so it's two different block writes. So maybe not the most efficient way to do this. So it turns out that using JSON to represent an aggregate is a really good fit. If you imagine what happens if you represent that movie and its images as a single JSON document, when it gets inserted, it's going to be a single block write. It's not going to be index maintenance. And when you read it, it's all going to come back as once, single block read. You don't have to have this agreement between the table definition and your Java classes anymore. Like the JSON can just take whatever field names you have in your Java objects. You get that schema flexibility. So if I want to add a field to my movie class, I don't need to go modify that movie table and so on. So you kind of get an easier experience and actually a more performant experience, sometimes significantly so. OK. So I wanted to end with a demo of some of the things that I've talked about here. And so this link here, everything I'm about to show is on it's on GitHub at this location. OK, so this is this code here is configured to create a database connection to Oracle Database 23. So in all my examples that I put here, I always set up this connection pooling, even though it's completely unnecessary in this case. And the reason I do this is in case somebody finds it and copies it, they have a hope of it performing well. Because with Oracle and many other databases, creating a new physical connection to the database is expensive because it has to open a new socket and it has to authenticate that connection. And so really what you want to do if you're doing repeated requests is pool your connections. And then for multiple SQL statements going across, you want to reuse those connections. But in here, since I'm only running one statement, it's unnecessary, but I just do that in case somebody copies it. So here, what I'm doing is I'm just creating a table called movie, just like was on the slide, with a column named data of type JSON. And so I'm going to run this now. So we see that that table's created. And so now I'm going to insert some movies into this table. So here, the beginning of the program starts out the same, but I'm compiling an insert statement. This is also pretty much the same as the statement we saw on the slide. And so I'm going to insert 4 movies. But for the example, I'm inserting the 4 movies 4 different ways. So the first one is what you might expect to see. I've got a Java lang string, and I'm inserting it, I'm setting it on this insert statement, and then I'm executing it. And so what happens underneath the covers here is that string goes into JDBC. JDBC sees, oh, they want to insert this into a JSON column. It converts it to this OSON binary format, sends it to the server just inserts it. So all the CPU cycles for encoding that are pushed to the client. The next one is inserting the next movie as one of these tree model JSON objects. So here, we're creating a new object, and we're putting the key value pairs into that object for the movie programmatically. And then again, we use the same statement. We set the object and then execute it. The third one is kind of like the first, but it's just taking the data as an input string from a file. And then the fourth one is maybe the most interesting. So the fourth movie we're inserting here is using this movie class. So movie here is just a normal POJO. It's about as vanilla of Java as it gets. And so we're newing up one of these movies. We're going to set the name to the Godfather, the gross sales, the genre, and then we're adding a list of those images to it. And so now, when I'm done with my object, I can just send it straight into the statement. So what happens there is, because I have that Jackson extension on the class path, it says, okay, here's some object I don't know about, so I'm going to use Jackson, converts it to this OSON format, and sends that to the server. One round trip. So I'm going to run this now. And it says 4 movies inserted. So let's read them back out here. So this is just selecting the column from the table, and it's should iterate 4 times, and it's printing out each of the movies it gets back as a string. So what happens under the covers here, it's never good to get your JSON data as a string like this. I'm just doing it for an example. But the OSON's coming back from the server, this binary format, and then it sees, oh, they want to have it as a string, so it serializes that OSON to a string and then prints it out. So we're going to lose the types, and it's not an efficient thing to do, but I just want to see it. So we can see 4 lines printed there of the 4 different movies that were inserted 4 different ways, but at the end of the day, OSON stored, and they came back to us, and we said, give them to us as a string. So what if I want to filter and get them back as one of these tree models? So now I'm saying, well, I don't want all the movies back anymore in this example, but I only want movies back where the gross sales is greater than some value. And so this is using those SQL JSON extensions where you can treat the JSON attributes as if they were columns in a regular table. So the first thing I do is I set the gross sales limit for this first bind variable, and then I execute it. And when I get the object back here, I'm saying I want it as one of these tree model instances. And then I'm able to kind of generically get the name and genre and sales out of this. And so this is using that in-place OSON access where it's going straight to that value without having to convert it to another form. And so there we see it only brings back 2 of the 4 movies. 2 are filtered out with the Iron Man and Interstellar. So I've just got a couple more I wanted to show here. So what if we want to get them back using the Jackson stuff? So here, it's selecting all the movies again. But now it's just sending in, hey, for each row that I iterate here, I want to get them as this movie class, this POJO. And I get the name and genre, and these are calling that kind of vanilla Java code that I showed you earlier. So if I run this, I apologize. I think I got it. OK, there she is. And so that's kind of at the core JDBC level. That's the idea. Like you can, issue these queries, either inserts, selects, updates, and you can, get the data or set the data very efficiently using this OSON format. But it's kind of most of the time happens under the covers for you. So there's one more example I wanted to show here. And so you can kind of get creative here. So in this example, I abandoned movies for the first time. And I'm kind of using a kind of canonical polymorphism example here, right? So I've got an interface, which is a shape, and it has a method area. And then I've got two records that implement shape. I've got a rectangle and a circle. So they both have areas, but they do it different ways. So the rectangle has the length and the width, and the circle has the radius. But both a rectangle and a circle are a shape. So if I wanted to store something like this, it might kind of be hard with relational, right? Because you have, you're storing different attributes depending on, which instance it is. If you wanted to store them in the same, collection or table. And so there's a nice interaction that happens here with record patterns. So the first thing it's going to do is it's going to create the table shapes, and it's just giving it, again, a single column of type JSON. And then it's inserting different shapes. So it inserts a circle, then it inserts a rectangle, then it inserts another rectangle. And they're all going into the same JSON column. And then when I read it out, I'm getting all these rows back from this data column. And each one, they're all going to be shapes, but some might be rectangles and some might be circles. So you can use this record pattern matching. Get it back as the shape, that parent interface. And then you can conditionally test using instance of whether it's a rectangle or a circle. So not only is this going to be efficient, but it allows you to handle these cases that might be more difficult with a fixed schema. So I'll go ahead and run this. And so it prints out the circle, rectangle, rectangle. The last example I wanted to show is with Spring Data JDBC. So this gives, if you recall back to what I was saying at the end of the slides about aggregates, this shows how that might actually work. Okay, so this is using a movies repository. And so movies repository is kind of empty. So it just extends this CRUD repository. And by doing that, it's going to give me a bunch of basic methods for interacting with the data. I've added one custom one here. So it didn't give me this find all by genre, so I said, I'm going to add find all by genre, but I'm going to give it this SQL definition here using this JSON exists function. So you can add your own, and you can still kind of add SQL where you need to, but for the most part, you don't have to. So if we want to insert these movies, and these are all this is just more vanilla Java code. So it's got a movie and movie details, and it's setting images. And then, so it inserts 3, in this case, Iron Man. But each time I want to, save these now, I'm just calling movies.save. I'm not having to, prepare those insert statements anymore. So it would insert those 3 movies. NoSQL issued. And Then after inserting them, it does a find all, and for each of the movies, it prints them out. It does a find by ID. It finds where the genre is equal to a value, and does various searches on this. And all of this is done without having to write a single line of SQL, or mostly. See the Spring app starting up, and then, sorry, I had intended to demo this using the debugger and show you bit by bit, but I'm having too much trouble with the controls here. So it inserted the movies, and then it was able to access them out, and NoSQL was used. So I think this concludes what I wanted to present and show. But the basic idea is you can do things like this, and they can make your code a lot more flexible. And actually, using the JSON for like the Spring Data example can make your code significantly faster, right? Because it's just minimizing the round trips, and it's minimizing the block reads and block writes, have fewer indexes on your tables, and so on. So it's not for everything, right? You still need, to normalize your data in places and, avoid duplication and all that stuff. But for things like aggregates with orders, line items, it can make a lot of sense. So I think that concludes what I wanted to show. So thank you for your time today. Any questions or?
How much you talk about Oracle specific? How much are
Yeah.
MySQL Postgres?
Yeah, that's a great question. The question was, if you couldn't hear it, how much of this is specific to Oracle, and how much is it transferable to Postgres and MySQL? And so it was very specific to Oracle, but as I said, they've all got their own binary formats. So I assume, definitely MySQL has similar capabilities. And one thing we're working on right now is we're trying to revive the JDBC standard and kind of standardize this so that using get object, set object, things like that, having a JSON type that you can pass, we'd start to get some conformance, among these relational databases. Yeah.
How would you do migrations on the JSON columns? So if I want to change an attribute, for example.
You mean change the name of the attribute? Okay, so the question is, how would you change the name of an attribute within one of these JSON objects? And so the SQL JSON stuff that I mentioned, but I didn't go into as much, has the ability to do that. So there's a function called JSON transform that has, you can say, you would basically do like an update statement, and you would set that column to the JSON transform of the column. And then there's a way that you can rename that field. And it does so atomically. So it either all renames or it doesn't. Yeah.
So it's a long process though, right?
Yeah, I mean, so with a database like Oracle, if you have a large table that you need to update, generating the redo and all that can take time because it has to do it atomically. So if you have like 1 billion rows or some massive table, you might want to batch that up and commit at intervals to, or if it's really big, what people will do is they can do a insert a select, right? So you create a modified copy of the data, and then that goes much faster than the updates would.
And one other question, does indexing come into play on this at all?
Yeah, that's also a great question. I was just cutting stuff, and I felt like I had too much. So yeah, so you can create indexes on these JSON attributes. And underneath the covers, it's the same indexing technology, B-trees, that is used on relational columns. So when you have an index column, you get parity with relational data for selecting those values. The one difference is that between relational and JSON is like, let's say I have an employee with addresses, and let's say I want to index the zip code. Now, each document, each row, can have multiple zip codes that need to be, put in the index. So for those cases, we have a special type of index called a multi-value index, where the same document, the same row, will be represented in the index multiple times. And then, then after that, it's just B-trees again. And we also support full text indexes, so you can do full text search over JSON. Does that answer your question? Yeah, okay. Anything else? Yes?
Does Hibernate support JSON operations?
These are great questions. So soon. There's a pull request. There's a pull request that we're still trying to get through the code review process, but I feel like it's going to land any day now. Yeah. But it uses like this Jackson stuff I was showing where it relies on that. So, yeah. Okay, thanks a lot for your time.